Okay, so the last few exercises you guys have on Khan Academy deal with limits. Limits are really what separates calculus and algebra. Algebra is very static, so we can look at the value of an expression or equation at a number, we can solve at a value, but it's very static. It doesn't really deal with things that are changing or that are dynamic. We can say, here is what the value would be right now. Calculus kind of is able to visualize how a system is changing by looking at the values that are around the current place, current state. So calculus gives us a much more dynamic sense of the world, how things are changing at a specific time, velocity, rate of change, acceleration. Really, a lot of physical properties are able to be found much easier using calculus, and the derivative and the integral, and the underlying foundation of those functions are limits. Limits are very simple. If I want to know what the function is doing, let's say at the value 3, then I'm going to look at things that are around 3 and try to figure out that pattern. So I'm going to look at maybe 2, 2.5, and like 2.9, 2.99, and kind of figure out a pattern that tells me what the function is doing at 3. So for limits, we're going to look at it graphically and algebraically. Now, the graph is easy because we can just kind of, oh, there it is. But let's look at a few things with limits. So we're going to start with limits intro exercise on Khan Academy. So here, the function h is defined for all real numbers. So here we have this graph of the function h. What is a reasonable estimate for the limit as x approaches 0? So it's the limit as x approaches 0 of this function. So I'm going to write that out so we can see it's the limit as x approaches 0 for h of x. Okay. The limit typically means a value. What's the value of h of x as we get closer and closer to 0 on the x-axis? Okay. Well, let's look. So like I said, if I want to know the value of 0, I could just look at 0, but we have two different values there on this graph. One way up at 5, and then one down here at -5. Okay. Now, we know the actual value, h at 5, here's a different color. So, algebraically, I can plug in 5. I have the closed dot. It is equal to 5. But I can see from the graph that there's something else going on here. Because a little bit to the left and a little bit to the right, and we get these huge divergences in that value. So I'm going to look at the limit instead. So, as x approaches 0, so I'm going to pretend like we can't actually see, that's not big enough. There's a shadow covering that line 0, so I can't actually see it. I'm going to ignore the actual value that we're looking at. Excuse me, not h at 5 is 0, h at 0 is 0. H at 0 is 5. Correct that, sorry. So now, I want to look. I want to look a little bit to the left and a little bit to the right of the value 0 on the x-axis. So I'm going to start here and here. And I'm going to work my way towards 0. One way from the left, one way from the right. So here, at -2, it's up here. So I'm going to work my way this way towards 0. And if I do that on the graph, I can see that as x approaches 0, my function is approaching 5. So we would say the limit as x approaches 0 from the left is 5. And using a negative to indicate direction left. On the right, as I approach that 0, so as I'm traveling along the x-axis here, you can see that what's happening to my function, the closer and closer I get to 0, the more it looks like -5. The limit as x approaches 0 from the right-hand side, indicated by this superscript plus, is -5. Since 5 does not equal -5, the limit does not exist. There is no reasonable estimate for the limit. These two sides of the curve are going to miss each other. Even though it's defined at 0, that's not how the system, the graph, is behaving. So if we go down and look at our options for this answer, the limit doesn't exist. There is no way to look at the left-hand side and the right-hand side of that graph around 0 and match them up. It does not exist. Now, here's the function h, defined at all numbers. We want to find the limit as x approaches -1. So the limit as x approaches -1 for h of x. So we don't really care what the value of the function is at -1. We want to know what is the behavior of the function around -1. So here's -1. I want to know what is the behavior of this function in a little bubble around -1. Let's make our interval a little bigger on the left here, right there. Okay. So I'm going to cut this function here, and I want to look kind of, what is the function doing in this region of the graph? Okay. Now, I can tell that h at -1, if I plug it in, h of -1 is equal to 4. I've got the dot, 4. But clearly the behavior of this function is not leading me to that value. That value is way up here. The graph is way down here. I want to know, if I'm on this curve, what should I expect to happen at -1? So I'm going to plug in values. From here, I'm going to move in. From here, what value should I expect? Even though there's a hole in the graph there, the limit as x approaches -1 from the left and from the right is -3. They're both approaching the same value. So where would these two ends meet? In the middle, it would be -3. On the other graph, the two ends never met. Here, a reasonable estimate for my limit would be -3. We're going to use that, -3. Is this the same? Table. So now, instead of a graph, they're giving me a bunch of numbers. But let's look at these x values. -6.1, -6.01, -6.001, -5.9, -5.99, -5.9. What's in the middle of all of that? It's -6. And surprisingly, that's exactly the value that they're trying to find. The limit as as x approaches -6 for this function. And so what they've done is taken some values of the function around -6. So -5.9, -5.99, -5.9. All of these are values that are larger than -6. So this would be the limit as x approaches -6 from the right, using larger values. -6.1, -6.01, and -6.001 are smaller values. So this would tell us the limit as x approaches -6 from the left, using smaller values. So for one side, we're coming in this way and trying to find that middle value. And then we're going to look at it on the other side and come in that way. It's like there are two sides to every story. There are two sides to every limit. Left and right, lower bound, upper bound. So if we look, as I get closer to -6 here, we have -0.25, -0.74, -0.98. I think the next one would be probably -1. And here, -2.3, -1.7, -1.02, -1 seems to match there as well. Since those are equal, since they're the same, it seems that as I went from the left to right, my sides matched up. That's my limit right in the middle. So a reasonable estimate for that limit would be that value that I think both sides are approaching, in this case, -1. Let's see if that's an answer choice. -1. C would be my answer. That's what I think it's going to do at that middle one. And this is the same. So let's move on to the next. Estimating limit values from graphs. Really, the next two examples, estimating limit values from graphs, really what you did on the limit intro. It'll give you a graph and you'll estimate it. And then one-sided limits we'll go over in this video as well. But here we go. The function h is defined, which means it has a value set for all real numbers except for 5, which we can see there is a hole in the graph. Okay? Cool story. What is a reasonable estimate for the limit as x approaches 5? So they're telling me here h at 5 is undefined, doesn't exist. But maybe we can figure out what it should be by looking at values around 5. So let's find the limit as x approaches 5 for h of x. Let's see what we get there. So taking 5, let's look at a neighborhood there. So I want to look at the graph. Kind of go towards that value, looking at those y values. And then here, same idea. Well, I can see, as I'm going from 3 to 5, as I'm approaching from the left, my values are getting closer and closer to something here, about 5.8-ish. And from the right, 7 to 6 to 5, as I approach that missing value there, it's the same. They're going to meet in the middle. They're not going to miss each other. One side's not going to infinity. They're going to meet right there. So that value, which I'm going to estimate to be about 5.7, about 5.7-ish. It's an estimate. I don't have any algebraic values that I can plug in, so I just think it's a little bit more than half, about 5.7, based on what I see as I look at the graph from the left-hand side, kind of moving in towards that value, and as I look at the graph from the right-hand side, again, kind of moving in towards that value. 5.7 is the value that we should see at 5. That's actually one of the answers. Cool. So let's look at this one. If it doesn't exist at 5, so we want to find the limit as x approaches 5 for g of x. And so there's 5. I kind of go a little bit to the right, a little bit to the left, and work my way in towards that value. But what I see as I move here, that's negative infinity. It's going down forever. But to the right, it's going to positive infinity. Are those two sides going to match up? No. Doesn't exist. If you cannot match the left-hand behavior and the right-hand behavior of the limit, it does not exist. In this case, to the left of the value that my limit is looking at, my graph is going down. To the right of the value that my limit is looking at, always approaching the value. So this is my center. So if I go to the right, I'm still looking that way towards 5. As I get closer to 5, my graph is going up. In this case, the limit doesn't exist, because the left-hand behavior and the right-hand behavior do not meet in the middle. So we would find the limit does not exist, which we have there. So that's all you're doing on the graphs. Okay. So now, let's look at one-sided limits from the graph. You notice that for all the limits so far, I've looked at the left and the right part of the graph. One-sided limits only consider one side, either the left or the right, looking at values that are smaller than x approaching, or looking at values that are larger than x and then approaching. You look at one-sided limits, left and right. Oops. Okay, so here, the function g is graph. So we have this graph here. I'm going to make this a hair smaller. We want the limit as x approaches 1 from the left. So this is the limit as x approaches 1. And then it has this kind of in the exponent place, that little negative there. That's the indicator of direction. So this would be g of x. That little negative indicates a left-hand limit, that I should only be concerned with values of x to the left of 1. So we're going to look at 1 here. 1 to the left would be looking only to the left. So none of these would matter. I can get rid of all of this. Doesn't matter. So my entire graph is now just this. And I want to try to approximate that limit only from the left-hand side. So I would look, as I go to the left and then work my way towards that value 1, the closer I get to 1 on the x-axis, the closer my value gets to 1. Okay. Now I can see that the limit itself wouldn't exist because on the right-hand side of this graph, this behavior is not going to match up with the left-hand side's behavior at all. They're not going to meet in the middle. So the limit as x approaches 1 doesn't exist. But the left-hand side of the limit is 1. This side, the left side of this graph, centered at the value 1, is going to 1. And so that's what we would look at. We're just looking at one side of that graph. A negative indicates the left-hand side, and we want 1. This one wants the limit as x approaches 1 from the right. G again, G of x. So again, if a negative in the exponent represents to look at the left-hand side, a positive in the exponent tells me to look at the right-hand side. So if we have a number line, this is the positive direction, this is the negative direction. And our limits should be going in. So if we have the limit as x approaches 1 from the left, we go to the left and look in. 1 from the right, and look in that way. This is 1 from the right, so we're only going to look at that right-hand side. We're going to ignore the left-hand side of this graph. So none of this really matters. I'm going to go out and say, okay, well, if I start moving in towards that value that we are interested in, what's my graph doing? So I'm like, So here, negative 7-ish, negative 7. The closer I get to that value, the closer I get to negative 5. That's my limit from the right. This is the value that I expect the function would have at 1 using values from the right and getting closer to 1 to try to approximate it. In this case, just negative 5. Negative 5 is the value. Again, the limit itself doesn't exist. This left-hand side and this right-hand side are not going to meet in the middle. So the limit doesn't exist. But if I only consider the right-hand side, I can approximate that value at negative 5. So that's what we're doing. We're only looking at one side of the limit. Hence the name, one-sided limits. So the rest is like that. You have negative and positive, left hand and right hand. And then connecting limits and graphical behavior. So here, which graphs agree with this statement? The limit as x approaches 1 from the right is 0. So effectively, if we have the point 1, 0, there, I need to find a graph that is approaching that from the right. That's what this is saying. I don't care what the left-hand side is doing, but the right-hand side needs to be going to the point 1, 0. So I need to first plot the point 1, 0 on these graphs, and then second, see, are they approaching from the right that ordered pair? So let's look at A. The point 1, 0 over 1 up 0 is right there. Is this graph approaching 1, 0 from the right? No, it's not. I'm assuming there are 4, so we'll see. So A doesn't work. Let's look at B and C. B, here's the point, 1, 0. As I move to the right, it's approaching that. B works. Again, I didn't look at any other part of the graph besides the point 1, 0 and the right-hand behavior. Is the graph pointing at that coordinate? C. Can't really see, so we're going to have to move it down. See if I get D on there as well. So B works. See, D is not above. So here's the point 1, 0, which on graph C, it's defined. It has a closed dot. But is that graph approaching that value? It's not. C doesn't work. D also doesn't work because B did work. So our only answer here is going to be B. B. Consider the graph of function f. Which limit expressions agree with the graph? So let's see what our limit expressions are. So the limit as x approaches 2 from the left of f at x is equal to unbounded, which means it goes to infinity or negative infinity. So that's 1. That's A. B. The limit as x approaches negative 4. Let's color code these. We're going to go back up to the graph. The limit as x approaches negative 4 from the right is 2. And then for C, the limit as x approaches 2 from the right of f at x is equal to infinity or negative infinity. And then D, none of the above. Okay. So now let's look at our graph. Yep. So for part A, we're looking at 2 from the left. So we need to find our point 2 here. From the left, it's unbounded. Which is true. As we go to 2 from the left, it does go to infinity or negative infinity. So that's right. Here, at negative 4 from the right, we should be pointing to a value of 2. So let's go look at negative 4. From the right, that is pointing to a value of 2. So that one is correct. And then, for our last one here, part C, at 2 again, but this time from the right, we want to see that unbounded behavior, which is exactly what we see. It does go to infinity or negative infinity. So our answer should be all of the above, or A, B, and C at least. So let's see. So A, B, and C all work. That's exactly it. So we're just looking for the limit from the graph. The easiest way is to look at it. Look at the direction that it's indicated. Positive means look to the right of the value and then approach that value. Negative means look to the left of that value and then approach that value. All right, guys, good luck. Get working on those. And I will post the last video, today's one,